Okay, people, I think we should begin all like here. So we are looking at, welcome to this class. We are looking at measurement of reactive species, quantitative measurement preferably. In the last class we looked at hydroxyl predominantly using dyes, fluorescent methods. We are looking at measurement in cell cultures, and we said that fluorescence method is easy enough for us to use it. We have been using fluorescent methods in our lab, fluorescence of dyes which are specific to specific reactive species. Of course, there are interferences, but they are reasonably specific. So for hydroxyl, which is what we saw earlier, we used APF and HPF. We discussed that, and then we looked at the various methods that are available, and I pointed you out to your textbook where the details of those methods are given. Okay, in the form of a table. The table is also available on your Moodle page. You can go and check that out. And then we started with superoxide. We said the fluorescent dye here is called hydroethidine, more commonly known as dihydroethidium. And the basic reaction is something like this: dihydroethidine, He, which is also called dihydroethidium. It reacts with one molecule of superoxide and gets converted to a product, and this product reacts with another molecule of superoxide and gives you the fluorescent product that we measure. Okay, 2-hydroxyethidium, right? Yeah, 2-hydroxyethidium is this product. And we said this is a two-step process. Therefore, you need 2 molecules of superoxide for every fluorescent molecule that is present. You need to keep that in mind if you are working on the quantitative aspects. And then you also need DNA, because the fluorescence comes because this product intercalates with the DNA and then becomes fluorescent. So without the DNA, that's not going to happen. You want to attend this class also, isn't it? Okay, yeah, so yeah, that's good. Good to sit through. That's nice. So fine. Any questions or comments so far? You all know that Radhika is your TA, right? Yeah, we introduced you in the first class. Then, but I don't expect her to attend. She has taken the course just last year. Okay. This was mentioned. The first step involving the reaction between superoxide and DHE to form the He radical, He dot plus, is a relatively slow process, 10 power 3 per molar per second, whereas the second step is fast, 10 power 8 per molar per, 10 power 9 per molar per second. Okay, so that is one aspect. Fine, you use DHE, you measure a certain fluorescence, but you'll have to relate that fluorescence level to a concentration of superoxide. To do that, you need a standard curve of fluorescence with superoxide concentration. Therefore, you need a stoichiometric method to generate superoxide and then measure its fluorescence and then relate the fluorescence value to the concentration, known concentration of superoxide. Okay. For a very long time, we were using KO2, potassium oxide. It's a reasonably stable salt, okay, rare stable salt of oxygen. And you just put it in water. There's a stoichiometric amount of superoxide that's generated. Okay, no problems. We've had very straight standard curves right through. So when Ranjani joined, and this was 2009, she graduated in 2014 or 2015. She wanted another method. I didn't care, as long as it is an acceptable method in the literature. I said follow it. So she somehow didn't feel comfortable with KO2. No reason, but it works well. She said, "Can I do this?" I said, "Yeah, as long as it is an established method in the literature, I have no problem. It works." So I'm just going to discuss that. Superoxide generation can be via the xanthine oxidase system. That's what she used. Various concentration of xanthine is oxidized by xanthine oxidase to generate different concentration of superoxide. And this also works well. This is the reaction. Xanthine is XA plus oxygen plus water in the presence of xanthine oxidase gets converted to uric acid, and you get this is stoichiometric, one mole of oxygen gives rise to 1 mole of superoxide only, but that requires half a mole of xanthine oxidase plus 2H plus. Okay, this is the basic reaction that happens. So you run this reaction, you generate superoxide, you measure the this is very stoichiometric and so on and so forth, so you get very nice standard curves with this. So the calibration curve is prepared by generating different concentrations of superoxide radicals and incubating the same with the dye. The final concentration uses 10 micromolar for more details at 37 degrees C for 30 minutes along with enough DNA. Okay, that enough DNA is initially calculated and then you multiply it by 1.5 and so on and so forth, just to make sure that it works, and it works most of the time. Any questions on this? So you have a standard curve which will give you fluorescence versus concentration. When you're measuring, you will measure fluorescence, and then you use a standard curve to link it to the concentration. In the case of KO2 plus water, that's it, pure water of course. It will give you the stoichiometric amount of superoxide generated. 1 molecule of KO2 gives you 2 molecules of superoxide. Sorry, 1 molecule of superoxide, the KO2. Yeah. No problem.
Final concentration of what?
Final concentration of the dye.
Of the dye.
Dye in the, right after the dye, final concentration of the dye is 10 micromolar. The excitation emission wavelength pair that we use in the lab is 405-570. There is a story behind it which I'm going to tell you next. Okay. The standard values are different, but the standard values give rise to a lot of interferences, and this is known from the literature. I'll also discuss that literature and then we'll go forward. Okay. So note this 405-570. The desired end product, its optimal wavelength pair is 480-580. Okay, whereas we are measuring it at 405-570. Okay. However, at 480-580, the fluorescence of the non-specific product, such as ethidium, will significantly interfere with the measurement. You remember the first step, right? First step, there could be other side steps. And especially ethidium, which gets formed as a part of this process, will interfere, and therefore you'd like to reduce the interference of ethidium when you're measuring 2-hydroxyethidium. Okay. Because 2-hydroxyethidium is the one that reflects the superoxide concentration. Ethidium doesn't. So to avoid interference, this wavelength pair is used, and this was given in the paper by Nazarevics 2012. I have a copy of the paper uploaded onto the Moodle page for you. You can take a look at the details. Okay, can you open that up so that it's easier to discuss? It's a PDF file. Yeah, I might as well go there and open it up, right? So you'll find it under support material, third file, DHE improved fluorescence method by molecular screening, Nazarevics 2013. Okay. Okay, what I'd like you to do is please read the abstract and browse the introduction. Okay, nothing more. Browse to the introduction. That must be, both must be readable, and then I'll discuss whatever I wanted to discuss. When you read maybe about 5-7 minutes, then we'll get back to this. Okay, you can read that. The whole paper is available. The main thing is this figure 1b. Okay, what you have here in figure 1b is the fluorescence ratio of the desired product to hydroxyethedium with the interfering product ethidium. Okay, this is the ratio. Therefore, the higher the ratio, the better it is. When you use an excitation wavelength of 480, then the variation with the emission wavelength, okay, you fix your excitation 480 and you scan the emission wavelength, the pattern, the fluorescence pattern is something like this. So you have, let's say 540, 530 and so on and so forth. You have a ratio of about 50 plus in this region. 52, is it? 52 in this region. Okay. So, whereas this inserted graph gives you fluorescence versus wavelength, the intensity of fluorescence. When you're measuring something, the intensity must be high enough for you to measure properly. Otherwise, there's a problem in measuring and so on and so forth. So, the idea is to have high enough intensity and a high enough ratio. Okay. If you use 480, 540, then yes, it is, although it's highly selective in terms of the ratio, the value is high, the actual value of the intensity is low. Okay. Low in the sense, in many cases, it's difficult to measure. If you use 405, 570, then this is what you have. Before that, if you use 405, 580, right, the intensity is high. That's the reason why it was chosen in an initial scan of 2-hydroxyethedium. But the ratio is much, much smaller, many-fold smaller, at least 10-fold smaller. Okay. So, you have a lot of interference from ethedium. Whatever you're measuring may not be superoxide and so on. I mean, superoxide purely and so on and so forth, or the interference is high enough to cause doubts. So, you would want to avoid this, although the intensity is higher. So, you use a 405, 570, where the intensity is high enough and the ratio is about 20, which is good enough, is what is, this is considered good enough, and therefore we use this. So, this paper is why we choose 405, 570 over the other optimal wavelength. Any questions on this? I will have this for some time then. So, at this wavelength, the ratio of fluorescence intensity is due to the desired product, and the undesired product is ideal. And this is part of the discussion itself. Whatever we just said, the absolute value of the fluorescence is considerably lower, and therefore we choose the other wavelength. Okay. The interferences He dot plus can be formed by other oxidants such as peroxidases and 1-electron oxidants. Okay. However, the conversion of this radical He dot plus to 2-hydroxyethedium can be brought about only by the reaction of superoxide. So, the second part of the reaction is specific to superoxide. The first part of the reaction is not specific to superoxide. So, this is one part of the interference. Non-specific products such as ethedium, E+, can interfere with the fluorescence signal from the desired product, and we have a way of handling that to a certain extent. So, that these are practical difficulties, but the data we get out of this is very useful. So, we believe it's okay. Okay, so that is as far as hydroxyl and superoxide go. So, we will just,
So, in times when we follow such protocols, we usually find that there has been an error. Does it mean whichever paper was published with those methodologies earlier are like false?
Good question. That's how science works. Okay. Science works by doing things to the best of our ability, and if proved wrong later, you just accept it. Okay, that's part of the process. It's always a self-correcting process. Many systems don't have this self-correction mechanism. Okay, when proved incorrect, rather that's a fully accepted part of science. Okay, yeah, we do the work. When we do the work, we do it to the best of our ability, and it is fully acceptable. It's not that, oh, you did that wrong. Okay, some media play will always be there, and so on and so forth. There are these stories that float around about some people. Let's not get into that. So, but apart from that, scientifically, yeah, that data is valid under those conditions. This was not even known at that point in time. Therefore, that's it. So the data, is there a way of correcting the data? Maybe, then you can correct it and reinterpret the data according to the correction. If it is not, then it has to be generated again, and so on and so forth, the correct. That's a philosophical question. That's part of science, fully accepted. Okay. So in fact, that self-correction is the most important aspect of science, is something that you would like to believe in. Each one to their own. Of course, it is not complete, and therefore you don't have to accept it fully, and so on and so forth. But be aware of the fact that it can correct itself, which is a great thing, which many things cannot do. Many dogmatic aspects cannot do. That's a tricky discussion, so I will not get into it. And usually personal. Okay. And as with hydroxide, superoxide can be measured by other methods also, and some of them are reduction in cytochrome C, reduction in nitro-blue tetrazoleum, light emission by luminol, light emission by luciferin, oxidation of adrenaline, and so on and so forth. This is also given as a file on Moodle, which is essentially an extract from your textbook. Okay, the same table is given there. I think the table goes as generation of superoxide, more for the standard curves kind of a thing. But same are the detection methods also. So take a look at that. Use whatever is appropriate for your needs. So all these are available. Be aware that many methods are available. I discussed in detail only the ones that we use in our lab. That's a given thing. Any questions or comments? Hydrogen peroxide, again, I will discuss only the fluorescent method and give you the other methods. Okay. There's something called Amplex red, which has a high sensitivity for hydrogen peroxide, which can be used, which we have used earlier. And it can measure hydrogen peroxide concentrations as low as 50 nanomolar. The principle is quite straightforward. This is your Amplex red. When hydrogen peroxide along with horseradish peroxidase, it's a peroxidase, therefore it will split hydrogen peroxide, and whatever is split from here will interact with this and give you this product, and this product happens to be resorphin, which is a fluorescent molecule. So you convert Amplex red into resorphin and measure it. And you need to add, whatever hydrogen peroxide is there in your sample, and horseradish peroxidase is typically added just to make sure that things are fine. You could have horseradish peroxidase in the sample also, but you add something extra for the assay just to make sure that it is done.
This turns into pink.
I thought it was more of yellow, if I remember right. Just double check. It's been a while since I saw that. Amplex red is reasonably red. That is fine, but the fluorescent part of it, Amplex red just looks red. See, this is fluorescence, right? So maybe it looks pink, but the fluorescence is in a certain range or something like that. 563, 587. That's the optimal wavelength pair for resorphin, and you set it and measure it for hydrogen peroxide. Hydrogen peroxide is very easy to measure. I just gave you a fluorescent method that we use, which gives you nice results. You can just measure absorbance at 280 to 40. The absorbance at 280 is protein, is it? 240 or 280, just check. When you don't use it for a while, you get confused. So the calibration curve, of course, you need to generate hydrogen peroxide of known values. So different concentrations of hydrogen peroxide, because you get standard hydrogen peroxide solutions, which are reliable. The reagent grade ones are reliable. Concentration of hydrogen peroxide are incubated with equimolar concentrations of Amplex red in 50 millimolar tris HCl buffer. These are just details, right? You can pick them up whenever there's a need. pH 7.4 containing HRP, horseradish peroxidase, 1 unit per ml at room temperature for 5 minutes. That's the procedure. The fluorescence is measured at 563, 587, and the interferences are all these interfere. Okay, you need to be aware of it, but usually these are handled. Not usually a major concern, but you should know that they interfere. And GSH is glutathione, as you know, NADPH, ascorbate, and superoxide. There are many other methods that are in a file, a different file on Moodle. Okay, take a look at that whenever there's a need. You just need to know that there are a lot of methods available. You can make a copy of it and keep it somewhere as a part of your notes. Just download that file, or you have access to the book. Then you don't. It's there in the book also. Only thing is that the exact. I think the book that you have in the library has this table only. Yeah, so that's okay. So earlier I used to take tables from an earlier edition. There are some additions to the current edition, so that is already there.